Wait, stop. Look at this bowl right here. It's just ice. Normal ice, sitting in a bowl, doing normal ice things. Now watch what happens when I add one ingredient that's sitting in your kitchen cabinet right now. Salt. Just salt. And in about 90 seconds, this bowl is going to get colder than a freezer. Not warmer, colder. And if that sentence just broke your brain a little bit, good. Because it broke mine too the first time I saw the math behind it. Because here's the thing. Your textbook never actually explained properly. It told you salt melts ice and just left it there. Like that's the whole story. Like case closed, mystery solved, go color in the diagram. But that sentence is doing something sneaky. It's hiding a contradiction so big that if you actually sit with it for a second, it stops making sense. If salt melts ice, shouldn't that make things warmer? Melting takes heat, right? So where's that heat coming from? If the water around it is getting colder instead, keep that question in your back pocket, because we are going to answer it. But not yet, because first I need you to understand something about how water actually decides to freeze. And once you get this, you will never look at a salted road, a bag of ice cream salt, or a science class diagram the same way again. Let's rewind to something you already know without knowing you know it. Pure water freezes at 0 degrees Celsius, 32 Fahrenheit. Everybody's heard that number 1,000 times, but water doesn't freeze at 0 because 0 is some magic cosmic constant. It freezes at 0 because that's the exact temperature where liquid water molecules and solid ice crystals are in perfect balance. Neither side winning, molecules jumping into the ice lattice at the same rate, other molecules are jumping out of it. It's a tug of war exactly tied. Now here's where salt crashes the party. When you dissolve salt in water, those sodium and chloride ions don't just float around doing nothing. They physically get in the way. They wedge themselves between water molecules and disrupt the neat, orderly lattice that ice needs to form. Ice is basically water molecules holding hands in a very specific, very picky pattern. Salt ions are like uninvited guests shoving into that formation, and the water molecules can't lock into place properly anymore. So the temperature has to drop even lower before the remaining water molecules can outcompete all that ionic chaos and freeze solid. That's freezing point depression. That's the entire textbook explanation. Salt water needs to get colder than 0 to freeze, sometimes way colder, down toward negative 21 degrees Celsius if the salt concentration is high enough. And that part, most people already sort of know. But here's the part they leave out, and it's the part that actually explains our bowl. When salt dissolves into water, it doesn't do it for free. Breaking apart that tightly bonded salt crystal and separating it into individual ions takes energy, real physical energy. And where does that energy come from? It gets ripped straight out of the surrounding water as heat. This is called an endothermic process, which just means it absorbs heat instead of releasing it. And when heat gets pulled out of the water, the temperature of that water drops. So now picture our bowl again. You've got ice sitting at 0 degrees, already at its melting point, perfectly balanced. You dump salt on it. Two things happen at the exact same moment. First, the salt dissolves into the thin layer of water on the ice's surface, sucking heat out of that water as it dissolves. Second, that same salt is now lowering the freezing point of that water, meaning it's no longer allowed to just sit there frozen at 0. It has to keep melting to find a new, colder equilibrium. It's not one effect, it's two effects stacking on top of each other, and they're both dragging the temperature down at the same time. This is your first pattern interrupt. So let's ground this in something you've actually tasted. Ice cream. Old school hand crank ice cream makers use exactly this trick. You've got your cream mixture in an inner container, and you pack the outer container with ice and rock salt. Not just ice. The salt drops that surrounding ice bath down to somewhere around -10 to -18 degrees Celsius, way below what plain ice alone could ever reach, and that's cold enough to actually freeze the cream mixture through the metal wall separating them. Without the salt, you just have cold cream soup. Same exact trick. Different century. This is also basically why your city dumps salt on icy roads in winter, except there they're using freezing point depression alone. Since roads aren't usually cold enough for that endothermic dip to matter much, they just need the ice to become liquid at a temperature where it would normally be solid. So cars stop sliding around. Okay, pattern interrupt 2. And this one's the twist that got this whole video started. Remember the contradiction from the very beginning? If salt melts ice, why does it get colder, not warmer? Here's the resolution, and it's kind of beautiful once it clicks. Melting itself is always an endothermic process, salt water or not. Melting ice into water always absorbs heat. That's just baseline physics. Ice cubes cool your drink specifically because melting steals heat from the liquid around it. Salt doesn't change that rule. Salt just forces more melting to happen than would happen naturally, by refusing to let the water refreeze at 0 degrees. More melting means more heat getting absorbed, which means a colder result, not a warmer one. Your textbook wasn't technically wrong when it said salt melts ice. It just forgot to mention that melting is a heat-eating process, not a heat-releasing one, and that omission is exactly what makes the whole thing feel like a paradox, when it's actually just incomplete information. Let's slow down and rebuild the whole picture from scratch, because I want this to actually stick, not just sound cool for 30 seconds. Picture water molecules as dancers trying to lock arms into a very specific formation. That's the ice crystal. At 0 degrees, they're right on the edge of being able to hold that formation. Salt ions are strangers shoving onto the dance floor, bumping into the dancers, making it physically harder for them to link up properly, for the dancers to still manage to lock into formation with all that shoving going on. The room has to get colder, meaning slower, meaning less energetic chaos before they can pull it off. That's freezing point depression visualized, and getting those strangers onto the dance floor in the first place, dissolving that salt costs energy too. Energy taken directly from the room's heat. That's the endothermic dissolving. Two mechanisms, same direction, both pulling temperature down. Now here's a mid-video twist that should genuinely surprise you. This effect has a hard ceiling. You can't just keep adding salt and get infinitely colder water. Once you hit around 23% salt concentration by weight, roughly the saturation point, adding more salt does nothing extra, because the water literally cannot dissolve any more of it. That magic number, negative 21.1 degrees Celsius, is the coldest a salt water and ice mixture can physically get using ordinary table salt, no matter how much extra salt you dump in after that point. Scientists actually have a name for this specific concentration and temperature combo. It's called the Eutectic point, the exact spot where you get the maximum possible freezing point depression for that particular substance. And once you know that phrase, Eutectic point, you start noticing this exact trick used everywhere. Airport runway de-icers aren't using table salt. They're engineered around different eutectic mixtures entirely, some using calcium chloride instead of sodium chloride, because calcium chloride's eutectic point drops even lower, working in temperatures where regular rock salt basically gives up and stops helping at all. Pattern interrupt 3. And here's where it gets a little wild. This same exact principle, forcing a substance colder than it should naturally be, is part of how some labs create supercooled water that stays liquid well below 0 degrees without freezing, because it has no ice crystal to latch onto and start the process. Add the tiniest disturbance, a tap, a speck of dust, even just pouring it, and it flash freezes solid in front of your eyes almost instantly. Different mechanism than our salt bowl, but the same underlying lesson. Freezing isn't just about temperature, it's about whether water molecules can actually organize themselves into that locked formation. And there are multiple ways to interrupt that organizing process. Let's bring it back to our bowl one more time, because now you can explain the entire thing yourself. Ice sits at 0, balanced. Salt lands on it. The salt starts dissolving into the surface water layer, pulling heat out as it breaks apart. That's step 1. At the same time, that dissolved salt lowers the freezing point of that thin water layer. So it's now sitting there as liquid water below 0 degrees, which physically forces even more surrounding ice to melt, to reach a new, lower equilibrium, and every bit of that extra melting drags the temperature down even further. That's step 2. Two mechanisms, one direction, stacking together, and that's how a kitchen ingredient turns a bowl of plain ice into something colder than your freezer. Here's the climax, the part that should genuinely mess with how you think about basic chemistry class. That single oversimplified sentence, salt melts ice, has been taught the exact same way in classrooms for generations, and it's not incorrect, but it's incomplete in a way that actively creates a wrong intuition in your head. It makes you picture salt as some kind of gentle heat source warming things up and melting them nicely, like sunshine on snow. The actual truth is the opposite. Salt is a disruptor, it's chaos in a shaker. It doesn't add heat, it forces the system to steal heat from itself. And the melting you're witnessing is really just water being dragged, kicking and screaming, into a colder and colder state, fighting to find a new balance point it never wanted to reach. And that single missing detail, endothermic dissolving, is exactly why ice cream makers work, why some de-icers outperform others in extreme cold, and why an entire eutectic point exists as a hard physical ceiling that no amount of salt can break through. One oversimplified textbook line hiding an entire branch of real thermodynamics underneath it. So next time you watch someone salt an icy sidewalk, you're not just watching ice disappear. You're watching a tiny thermodynamic tug of war, ionic disruption on one side, heat hungry dissolving on the other, both teaming up to force water into a state it would never choose on its own. That's not a simple textbook fact anymore. That's real physics happening in your driveway. If this rewired how you think about something you assumed was already explained back in 5th grade, that's exactly the kind of thing this channel exists for. Hit like if your brain just did a little double take. Subscribe if you want more of these hidden contradictions, hiding inside stuff you already knew, and drop a comment telling me what everyday thing you want broken down like this next, because there is a whole list of obvious facts out there that are secretly way weirder than they look. See you in the next one.